So 4.5 takes a turn. So we've just finished not rational functions. We've just finished polynomial functions. So 4.1 to 4.4 is polynomial functions. End behavior, x-intercepts, how to solve for those x-intercepts or zeros or solutions to the equation, and then how to graph using them, using their multiplicity or using intervals. Now we're going to do the exact same thing for rationals, but in one day, because we're going to do much less of them. So first off, you need to be able to define a rational function. So a rational function is a function formed by the quotient of two polynomials. And the key thing for me is that as soon as you're rational, you're going to have a polynomial in the denominator. So a polynomial function has 1 in the denominator, and a rational function has an expression in the denominator. And one of the key components is that as soon as you have an x in the denominator, you have to be careful that whatever you put in for x does not make your denominator equal to 0. So the domain of a rational function is what x values it could be. So x can be everything but the things that make the denominator equal to 0. Now, the new part is going to be talking about vertical asymptotes and what that feature does to a rational function. So a vertical asymptote happens because there's values of x that don't exist. So if I look at a function like y equals, or f of x equals, 1 over x minus 3, I could look at this and determine the domain. The domain is that x minus 3 cannot equal 0, so x cannot equal 3. Well, what does the graph do around that value of x equals 3? Well, if I look at what x equals 3 on my graph, where it exists, this is the vertical line, x equals 3. What is my graph doing? Well, my graph is approaching this line, but never quite reaching it. Algebraically, to see that, if I put in values approaching 3 from the left and then approaching 3 from the right, you can see what the graph does. So if I approach from the left, so if I put in an x value of 2, I get a y value of negative 1 right there. If I put x equals 2.5 into this equation, I get y equals negative 2. If I put 2.9, I get negative 10. I'm way down here. If I go even closer to 3, 2.99, I get negative 100. 2.999, negative 1,000, negative 10,000, negative 100,000. As x gets closer and closer to 3, the value for y gets closer and closer to negative infinity. This is called asymptotic behavior, right? So this graph is approaching a number, but it's never going to reach it. It's never going to get to x equals 3. So what does your graph do? Your graph goes down to negative infinity. Same thing if I approached positive 3 from the right. So if I started here at x equals 4, I get a y value of 1. If I put in x equals 3.5, I get a y value of 2, and then again 10, 100, 1,000, 10,000, 100,000. This graph is approaching positive infinity. That's its asymptotic behavior, this approaching infinity or negative infinity as you approach a certain x value. We call this line that you're approaching but don't cross in this circumstance, we call it a vertical asymptote. So this line, x equals 3, is a vertical asymptote. It's an invisible line. It's not part of your graph. I'll often show them with these dotted lines, but they are not actually there. They do not actually exist. They're just this invisible line that you approach. Okay, so let's look at some different graphs and some different asymptotes. So first thing I want to look at is f of x equal to 1 over x. This is my graph. So if I was to ask you right now, what's the domain of this function? You'd say, what are the values that would make the denominator equal to 0? So x cannot equal 0. This is set notation. I mean, to make it proper set notation, according to this textbook, you would just go the set of x such that x cannot equal 0. Or you could show this in interval notation, which would be that x can be everything from negative infinity up to 0, or from 0 up to infinity. So I don't care which way you show it. The textbook starts off by showing both, and then eventually they go to straight to interval notation, which is unfortunate because set notation just makes so much more sense. Okay, so the domain is that x can be everything but 0. So what happens at x equals 0? Well, you get a vertical asymptote. The vertical asymptote would be here at x is equal to 0. So x is equal to 0 is the vertical line that your graph approaches because your graph cannot equal 0. Same thing here. If I asked you the domain, you'd say, well, what would make x squared equal to 0? Well, if x equals 0. So x cannot equal 0. And again, that's the equation of your vertical asymptote. There's a line here at x equals 0 that your graph approaches but cannot touch. Same thing here. We've got f of x equal to x minus 3 over x squared plus x minus 2. I want to know what would make my denominator equal to 0. So the first thing I'm going to do is factor. So that factors to x plus 2 times x minus 1. What would make either of those factors equal to 0? Well, x cannot equal negative 2 and x cannot equal 1. If I look at that, here is negative 2. There's that line that you're approaching but never touching. And here's the other one at x equals 1. So those are the equations of my asymptotes. The asymptotes would be x equals negative 2 and x equals positive 1. All right, pause the video, see if you can do this next one. Okay, so for this one, again, the factor in the denominator that has an x is x minus 3. So x cannot equal positive 3. What happens there? Well, you get a vertical asymptote. X is equal to 3. So if I drew a vertical line through x equals 3, you can see the asymptotic behavior of your function about that asymptote. So that's it. That's vertical asymptotes, and they are super duper important for what we're going to be doing next. I just have to show you one exception. So the exception is that if I give you an equation like f of x is equal to x times x minus 4 over x times x minus 1 times x plus 1. If I asked you the domain, you would tell me that x cannot equal 0, 1, and negative 1. Okay, negative 1, 0, 1 if you're writing them in numerical order. So this is my domain. These are the things that x cannot equal. But if I go over here and look at the graph of this function, what I want you to see is that there's only two vertical asymptotes. There's one here at x equals negative 1, and there's another one here at x equals positive 1. Should have made this graph a little bit bigger, right? There's these two vertical asymptotes, x equals negative 1 and x equals positive 1. Well, wait a minute. There was 3 places that my domain didn't exist, but this only translated to 2 vertical asymptotes. And that's because if you look at this function in factored form, so x squared minus 4x factored to x times x minus 4. Your denominator, right, x cubed minus x would factor to x squared, or sorry, not x squared. Right, I can't undo. X times, so the greatest common factor was x times x squared minus 1, and then I'm left with the difference of squares. So it's x times x minus 1, x plus 1. If you look back to this original function, hopefully you see that there's a common factor between the numerator and the denominator. There's this x over x. X divided by x is 1. It's a common factor. So it's not actually going to turn into a vertical asymptote because that part of your graph can actually be excluded. Like when I go to graph this, I'm actually going to graph x minus 4 over x minus 1 times x plus 1, right? I'll take that x out of it. But this x did exist. So what does it do to my graph? Well, what it does is it puts a hole. Now, really hard to see the holes. In fact, I'll show you this on Desmos. You can't see the hole, but you're going to have a hole at 0, 4. Why 0, 4? Well, when x equals 0, so if I was to put into this new function, x equals 0, right? Because I took out that thing that made it that x couldn't equal 0, if I put it into what's left, so 0 minus 4 over 0 minus 1 times 0 plus 1, you can see that I would get negative 4 divided by negative 1 is positive 4. So when x is 0, y is 4. There's this hole at 0, 4 that on a normal graph and in Desmos you won't see, but we're going to make sure we know is there. So if I show you what happens in Desmos, I already plugged this in. This is the graph, right? If I wanted to see the asymptotes, I could put in an equation x equals 1, and I could put in an equation x equals negative 1. Oops, negative 1. To show that these are not part of my graph, I'm going to put them in as dotted so they don't actually exist, right? So these are lines that my graph approaches but doesn't cross, and there is not one of these at x equals 0. So what happens if I scroll in? Well, if I scroll in and I look at what happens when x equals 0, you're not seeing anything. But look what happens when I put a table of values in there. When you look at the table of values for this graph, look at what happens at x equals 0. When x equals 0, my graph is undefined, just like it's undefined when x is negative 1 and x is positive 1. So this x equals 0, right? There's this break in the graph, but you'd have to scroll in so far to see the break. You know, your Desmos doesn't just put like a big circle to be like, hey, look, there's a hole here. They would actually want a hole. And I scrolled in class today and couldn't get there where you'd see the hole. But I have faith that at some point you'd scroll in enough that, you know, it wouldn't exist at 0, 4. Okay, so just trust me that your graph does not exist there. There's a hole, but you're not really going to see it when you're graphing, and it's not going to affect things much when we do this on Thursday. Okay, so let's practice just that. So I want you to pause the video and determine the domain and the vertical asymptotes in the function. So remember, the domain and the vertical asymptotes are the same unless there's a common factor between your numerator and your denominator. All right, welcome back. So hopefully you get these right. So if I look at the domain of this one, I just look at the denominator, okay? In this factored form, I'd say that x cannot equal 0, 3/2, and -1. And in a perfect world, I would write that in numerical order, right? -1, 0, and 3/2 because it's easier to read, but that's how it comes off of here. My vertical asymptotes, which I'll just shorten to VA, my equation, my vertical asymptotes would only be 3/2 and -1. Because this x is a common factor that would go away, that would, divide out, right? And so I'd be left with x squared over 2x minus 3 times x plus 1. That's what I'm going to graph, and then I would have a hole at x equals 0, right? If you want to find what the actual hole coordinates are, you could plug in, I should do that as f of x. You could plug in x as 0. So if I go f at 0, this isn't an f, this is an h. So if I do h of 0, I would, into this new function, get 0 squared over 2 times 0 minus 3 times 0 plus 1. Now, no matter what, I have a 0 in my numerator. So 0 over anything, what does this end up being? -1 times 1 over -1. The hole's at 0. So I would have a hole at 0, 0, right? There would be this place, but it's not an asymptote. It's just a hole in your graph. Okay, this one, if I look at the domain, again, you're just looking at that denominator. X cannot equal 0, √5, and -√5. There's no common factors between my numerator and my denominator, so my vertical asymptotes would be 0, √5, and -√5. All right, so that is vertical asymptotes. The next thing we need to look at is called horizontal asymptotes. So a horizontal asymptote, instead of being an invisible vertical line, it's an invisible horizontal line. But there's a very key distinction between a horizontal asymptote and a vertical asymptote. Vertical asymptotes are absolute. You cannot cross a vertical asymptote. Your graph stops at them every single time. Unfortunately for horizontal asymptotes, they're kind of a suggestion. They're a horizontal line, or an invisible horizontal line, that certain functions approach and sometimes cross. So sometimes your graph has asymptotic behavior around these horizontal asymptotes, and sometimes it doesn't. Okay. Now, how do you find a horizontal asymptote? Well, a horizontal asymptote is found as with a limit. So you're going to have x approach infinity and see what happens to your graph. So if I pick x values that are getting closer and closer to infinity, so I'm going to pick 100, I'm going to pick 500, I'm going to pick 1,000,000. Look what happens to the y value. As I put a bigger and bigger value in for x, I'm dividing by a bigger and bigger number, which means that my graph is getting closer and closer to 0. So if I do 1 divided by, what would this be? Ooh, 999,997, right? Because I just have to subtract 3. I'm getting closer and closer to 0. So my graph wants to get to 0, but now no matter how big I make this x value, it's still going to be 1 over something. So it's going to approach 0 but never reach it. So as x goes to infinity, my y value approaches 0. Okay? As your graph approaches negative infinity, same thing, -300, -800, -1,000, your graph is again going to approach 0. Because as I put a bigger, like a larger and larger, I guess I should say smaller and smaller negative number in here, I'm getting a number that's 1 divided by this massive negative number, meaning I'm going to get closer and closer to 0. So if you look back at this graph, This is that y equals 1 over x minus 3 graph. Now you can see that there's another asymptote. There's a horizontal asymptote here at y equals 0, which will be a line that your graph will approach, and it does not cross in this circumstance. I'll show you in a bit which ones do cross. Okay, so that's what a horizontal asymptote is. It's what, as x approaches infinity or negative infinity, what does your y value approach? All right, now to make things more complicated, horizontal asymptotes are not straightforward. Okay, to find a horizontal asymptote, we're going to look at 4 different scenarios, and it's all going to be dependent on the degree of your numerator and your denominator. So scenario 1 is when the degree of the numerator and the denominator are the same. So something like 3x squared plus 5 over x squared minus 1. This is your leading term of your numerator. This is the leading term of your denominator. Since the degree on x is the same, we're going to find the horizontal asymptote by doing the following. You are going to find the equation by saying y equals a over b, where a is the leading coefficient on the numerator and b is the leading coefficient on the denominator. So if I look at this one, the equation of the asymptote would be y equals the leading coefficient in the numerator, which is 3, divided by the leading coefficient in the denominator, which is 1, and I'd have an asymptote at y equals 3. So I already generated these in Desmos, and keep in mind, if you generate these in Desmos, these dotted lines don't show, right? Because the blue is the graph. The blue is your rational function. These asymptotes are guides, but they're not part of the graph. So I've put them in so that you can see them. I wanted you to see your graph approaching y is equal to 3, right? Y is equal to 3. It also has 2 vertical asymptotes because your denominator would equal 0 at x equals negative 1 and x equals 1. Okay, so this graph would have 2 vertical asymptotes and this 1 horizontal asymptote at y equals 3. Scenario number 2. Scenario number 2 is when the degree of the numerator is less, doesn't matter how much less, but less than the degree in the denominator. So if you have like this, the degree in the numerator is 1, the degree in the denominator is 2, right? So the denominator is greater. Here's the best one. This one's so good. This is the only one we're going to sketch. Okay? When you're sketching rational functions where the degree in the numerator is less than the degree in the denominator, y equals 0 is always your asymptote. Okay? So this y equals 0 is always going to be your asymptote. Now, those are the ones we're going to graph, but there's 2 more. The next one is when the degree in the numerator is 1 degree greater than the denominator. So if you have something like x squared over x, then your your asymptote, which is actually no longer horizontal, it's actually called oblique or slant, is this oblique or slant line. And to find it, you actually do long division or synthetic division. But you take the numerator and you divide it by the denominator, and the quotient is the equation of the slant asymptote. So it's cool. Like it makes this section tie into the rest of chapter 4. But it's not necessary for where we're going in 4.6. So we won't be graphing these, but total extra credit. You know, if you're interested, feel free to graph all of these, right? What does it look like? How do I sketch something that has an oblique asymptote? How do I sketch something that has this horizontal asymptote at y equals 3? But we are going to be practicing graphing ones that have a horizontal asymptote of y equals 0, just to keep things simple and to make you understand the points that we need for 4.6. And then lastly, if the numerator is greater than the denominator, and not 1 greater, but like more greater, there is no horizontal asymptote, just to make things really fun. All right, so this is the first video. Go and practice those 4 questions in your textbook before moving on.